Hello, everybody. There's a lot of feedback happening, I'm sorry. Okay, so I'm Chris Martens. I'm a grad student at Carnegie Mellon University in Pittsburgh in the computer science department there. So I'm still an academic. I haven't recovered yet. And I'm really happy to be here at Strange Loop. This is my first one to tell you about linear logic programming, which is sort of the basis of my PhD research. Okay, so this is just to give you a parse on the title of my talk. It's kind of a word-level portmanteau of the concepts of linear logic and logic programming. And I'm going to sort of assume at least a little bit of familiarity, like maybe you've seen or heard of logic programming, which I mean to be broadly queries on sets of rules. But that linear logic may be a more unfamiliar concept. Linear logic is just a variant on propositional logic that's good at dealing with resources, at least at a very sentence-level brush. And the key point of this talk, basically, is that a system based on linear logic programming is really good for expressing what I'm going to call locally stateful computation in a declarative fashion. So what I mean by locally stateful is that you're trying to model some evolving system, like maybe you're trying to describe the space of allowable moves in a board game or something. And your state consists of a bunch of stuff. So you've got all of the cells of the board game. You've got maybe some other global properties of the game that you're tracking, like whose turn it is and whether certain pieces have moved yet or whatever. And when you're operating on the level of a single move in the game, you're really only interested in certain properties changing. And for instance, if you're moving a pawn, you only really want to care about the square that piece is on and the squares sort of directly adjacent to it that it wants to move to. This is sometimes described as a frame property in other settings. So I'm an ivory tower academic, like I said. This is going to be a pretty theoretical talk. I hope that's okay. The research group I'm in is called the Principles of Programming. So, the first sort of obvious thing that I hope you get out of this is that maybe there are some broadly applicable concepts to whatever you're working on, or if you happen to do research, whatever you're researching. The second is that there is an implementation of these ideas. I wouldn't exactly call it an emerging language. It's kind of a happy hermit of a language called Celf, which is kind of just a really bare bones implementation of these ideas just to kind of play with them. But I think it's really fun and a neat thing to use and extend potentially in the future, which is my third point. I want to see how these ideas can grow into something like maybe a library like CoreLogic is used in Clojure for logic programming, maybe something like that, where it can be used as an embedded language in a more fully featured setting. Or another way of possibly positioning this in the future is as a scripting language, or some other part of your toolkit for a development process. Okay, so back to this idea of locally stateful computation. Just like a very kind of naive gloss of things, just to give you some idea of what I'm talking about in terms of settings you may be more familiar with, there's a purely functional way of processing, of dealing with state like this, which is just to pass the entire state around through your function calls. So this is just sort of the standard way of doing functional programming with big data structures. Of course, there are ways to improve on this, but this is the naive way of doing it. In the imperative setting, in the imperative setting, we can just do this direct kind of in-place replacement of some state with some other state, which is the notion of locally stateful computation that I'm describing. But what linear logic programming gives us is a declarative approach to that. And declarative is an awfully fuzzy word. So let me try to be more precise about what I mean. So I'll start by giving you another fuzzy word, which is high level. Okay, what I mean by that is that there is a really close match between the ideas that you're trying to represent, like the state of your system, and the constructs that are available to you in the language. So I really want there to be a direct mapping between those things. And the second thing I mean by declarative is that it's informed by logical principles. I really like logic, and I happen to think that it's a great way of sort of organizing your ideas to design a language in the first place. It has a lot of good guiding principles so that we know when we've gotten things right. So that's why I like logic programming. Okay, so what do I mean by logic programming? The analogy that I love to use to explain logic programming is that proof search is execution of a program. So you have some program that just is describing some. I am worried that I got these slides out of order. I might just be missing some. Okay, gonna run with it. Okay, so a logic program is a set of rules and a query. So the thing on the box to the left is the set of rules, and the thing in the box to the right is a query. And these rules, the syntax of this rule just say that there's a rule called rule 1, which establishes A of foo from no assumptions. So that's an axiom. And there's a rule called rule 2, which establishes B of x from A of x, where x ranges over anything. It's universally quantified. That's what this symbol for all x means. And a query is something that you can run after you've written the program. You can ask the program is this thing true? You can say, is B of x true? And really what that means is for some x, is there some value that you can put there that would make the thing succeed? And if it can, it might succeed in a variety of ways, but if it can, it will give you a value for that x, for in this case foo, and if it fails, it will tell you that it's failed. And in addition to giving you an answer, what's the value of x, you also get a proof, which is just this composition of rule 1 and rule 2, demonstrating the fact. Okay. So here's a sort of more realistic example, but still quite small example, of how to use proof search as computation. Again, this is just sort of prologue-style logic programming, so this is review if you've seen that, at least in terms of the way the program is written. So this is a program that computes graph connectivity, and we have a rule that says if there's an edge in our graph from x to y, then there's a path from x to y. So that's one rule defining path. And there's a path transitivity rule, which says if we have an edge from x to y, and then that's some intermediate point y, a path from y to z, then we get the composed path from x to z. And when we want to encode some test program, like this linear graph that goes a, b, c, d, we're able to encode that as just yet more rules in our system, and in particular as axioms that don't require anything, where we establish that there's these edge predicates between AB, BC, and CD. All right, so there are, if we wanted to think about this idea of proof search, how we would implement it, there are kind of two complementary ways of talking about it, and these aren't mutually exclusive, but they can be sort of explained as separate strategies. And these are, I'll call them backward chaining and forward chaining. And if we run some query, this question mark dash syntax again is what I'm using for queries. If we run a query trying to search for some goal, then in the backward chaining setting, we'll look at that goal and we'll start working upward. We'll start saying which rules in my program match that goal, and then try to solve recursively for those subgoals. Forward chaining, so that's the way the prologue works. So forward chaining is kind of an alternative approach where you start by just looking at your program, you look at the axioms that you already have, and you start propagating forward, just trying to fire your reasoning at everything in sight until it doesn't make sense to anymore, and then you stop and you see whether there's anything in your context that matches the goal. Yeah. Okay, so this is an illustration of, in particular, how forward chaining works. And I'm going to, I wish I had some way to slow reveal this, sorry about that. So the query, if we run a query on our graph connectivity program, searching for the query path A, x, where x again is this existentially quantified variable. This is supposed to return to us all of the values all of the things that are reachable from A. Right? So what forward chaining does is we give it that query, and it's like, OK, that's nice, I don't care. I'm just going to look at the program and first pull out all of the edge facts and throw them into something that I'm going to call a database. Then we want to apply every rule that can apply to those facts to everything in our database. So we add in the path facts corresponding to each of those edges. And along the way, maybe we notice that there's already an answer to our solution. But we then do this again, where we generate the path facts that now can be generated from the previous edge facts and the new path facts, which gives us the 2-hop away connectivity. And then we keep doing this until what I call saturation, which is the point at which applying some rule in our system would not tell us any new information, anything that we don't already have in our database. At saturation, then we can go back and look through, and we can notice that B, C, and D are all values of X that make that true. Okay. So I've told you that Prolog, which is kind of the most popular, successful logic programming language, it uses backward chaining. So why would we care about forward chaining? People care about it for different reasons. This is just a little bit of context for it. David McAllister has proven some complexity results for certain classes of programs that just work a lot better using the forward chaining approach. Like, for example, the program I just showed you, you get a kind of memoization for free by eagerly computing all of these subprograms. And as opposed to the backward chaining approach, where you recompute them for everything that shares a subproblem. In the database community, there's a system called datalog, which is kind of a generalization of SQL. And I don't know that much about it, but I know people like it. And what I'm actually interested in, why I'm interested in forward chaining, is because I want to be able to model evolving systems. So to explain how we get from the forward chaining that I showed you before to how you'd use it to model an evolving system, I want to look at a little bit more carefully at this way that I'm thinking of rules as propositions in a logic. So previously I was writing rules with 2 premises and a conclusion like this. And you can think of that as a formula in first-order logic. So if you can just read the syntax if you're not familiar with it. It says, for all x, a of x and b of t implies c of x and t. And these connectives, as for all, implies, and are connected in first-order logic. And this is sort of the ambient logic in our system, which I will call the host logic. That's kind of just to distinguish between the fact that when we're writing down systems in a logic programming language, those themselves can that system can be kind of thought of as a logic, as like the object logic that we're encoding. And I'm differentiating that from the host logic. So the idea of this talk is basically to replace the host logic, or at least add to a host logic, constructs from this other logic called linear logic. All right, so I'm going to explain linear logic by sort of contrasting it to the typical notion of logic that you may have seen before. So persistent or truth-based logic is kind of what we care about as human reasoners, right? So we're trying to learn things about the world, and we know that someone tells us that gravity causes things to fall. And then we separately learn that gravity exists. So we cleverly deduce that things can fall. But we don't forget that gravity exists. We just add that to our store of knowledge that we're accumulating. This makes sense because these things are thought of as facts that never change, never go away. Linear logic is resource-based. So instead of facts, we have things like $1 or a snack that are more like things that we spend that get consumed. So there's an analogous concept of implication with this lolly symbol and with this tensor symbol, except that they kind of mean different things when we're thinking of our logical atoms as resources rather than facts. So in this system, it's like if you have some way, like a vending machine, of turning $1 into a snack, and you also have $1, then you can get a snack, but you don't get to keep the $1. Sorry. Okay. So from the logic programming side view, I had been describing the way that the system, the forward chaining system evolves as like a database. And so, you know, it's like you're running around with a notepad, you're like an alien, you're trying to learn things, and you have this notepad and you write down the fact that the gravity exists, okay? And then you also have this inference that gravity causes things to fall, so you write down things fall at the bottom. So your database is monotonically increasing is kind of the mathy word for that. It just keeps growing. Instead, if we think of this rule as like for turning a dollar into a snack as a linear logic proposition, and we want to kind of change the state along that proposition, then well, we have $1 and maybe some pocket lint in our pocket, and maybe we have another $1 too. And when we change that state via that rule, well, we should replace one of our dollars with a snack, but everything else kind of stays the same, including that other $1 that we didn't spend. All right, so I've talked about the way that we use linear logic notation to conjoin two resources, A tensor B, and A lolly B means basically replace A with B. There are two other connectives that are important in this logic. Bang A is the way that we refer back to something that's persistent, so we can still recover all of the stuff that has to do with facts as well. And then there's just a symbol, bold 1, that just means the nothing resource, the empty resource. And I've so far described both forward and backward chaining and persistence and linear logic, and all combinations of these things make sense. But specifically for this talk, I'm going to just kind of by convention and by virtue of the examples I'm working with, use backward chaining predicates for persistent things and forward chaining predicates for linear things. And again, that bottom left cell is really kind of what I'm interested in, because that's what lets us model these evolving systems. Everything with a green check mark in it is available and supported in Celf. It doesn't really have good support for doing persistent forward chaining, but that is something that's available in Datalog. Okay, so now I just want to try to give you a bunch of examples of like how you would actually write and run a program like this, what that would give you, and then just try to expose you to a bunch of examples so that it gets in your head a little bit. And by the way, everything in this talk is runnable, or at least there's a version of it that I've coded up all these examples. So if you want to like find me afterwards and see the way the system actually looks, that would be fine too. Okay, so my first example is sorting. And in particular, I'm going to talk about a sort of silly sorting algorithm where we want it to be in place, and we basically just want to do it by looking anywhere where there's a pair of adjacent things that are out of order, and then just swap them. So we want to like reach in anywhere into like the middle of our array, notice that 10 and 3 are out of order, and swap them. Okay, so the first thing that we're going to write in our logic program just looks like straightforward, persistent, backward chaining. So standard kind of prologue style definitions where we have these adjacency facts establishing which locations are adjacent, and we have a recursively defined predicate on numbers that defines when something is less than another thing, natural numbers. And now we can actually write a sorting program in one line. Okay, so the way this works, so this is a forward chaining linear rule. So we consume the fact that n is at the location L, and then we notice, using the backward chaining predicate for adjacency, that L is adjacent to L prime, and then we see we also consume the fact that n prime is in L prime, and we notice that n prime is less than L prime. Okay, so the things I've said we've consumed, those now go away, and they get replaced with what comes after the lolly, which is now we put an n prime at L and the n at L prime. So just literally just reordering the two components of the array, only writing down, again, this is important, like only writing down the bits that we cared about. Okay, but how do we actually use this to like run a program? So just a tiny example. So if we have locations L1 to L2, L3, and we have 3, 2, 1, then we can write a query. Now this is a sort of a different form of query than I was showing you before, because we actually have to write it as an implication. And the reason for that is because these at atoms, these things that say which values are at which locations, those can change. Those are linear resources. So if we just wrote them down in our program, they'd be taken as axioms and considered persistent. So we kind of have to preload our initial state by writing it all to the left of the lolly. And then we can say, now at the end of that forward chaining phase, I expect there to be similar predicates in the state. I'm going to be using the word state where I was using database before, so the state of linear proof search. So I expect my state at the end of proof search to look like this, where x1 and x2 and x3 can range over whatever they happen to be at the end. And instead of talking about saturation like I had previously done for forward chaining, I'm going to talk about quiescence, which is analogous, but in terms of linear logic, it doesn't make sense to say just because if we fire a rule, we get something that we already have in our database, don't fire it, because we might still want to fire it because extra copies can help us. Extra instances of $1 are different from one instance of $1. So instead, we stop doing linear forward chaining when there just are no more rules that can fire. Okay. And you might notice that in this example, there are actually two locations starting out where this swap rule that we've written applies. So there's sort of two adjacent things that are out of order. And in the persistent view of the world of forward chaining, we would just be doing both of them anyway, and it wouldn't matter which order we did them in. But in linear logic changes the world. So when we apply some linear rule, we may not be able to apply the other one again. So we have to actually pick which one. And the way that Celf does this, the sort of semantics that we've decided to give this, is just that it's non-deterministic. It just picks one. Okay, so this means that there are actually two different ways that this that the sort could happen. So we could first swap 2 and 3, and then 1 and 3, and then 1 and 2, or we could swap 1 and 2, and then 3 and 2, 3 and 1, and then 3 and 2, and then 2 and 3. And all of the things in teal are kind of just carried through because they're not, those are the frame part of the frame property that I was mentioning. They don't matter to the rule when we're applying them. In terms of the actual software, you get something that represents sort of that graph I just showed you in a more kind of lambda calculus-y notation, if you like that sort of thing. That's what we have. And this is literally just a proof. I mean, it's a proof exactly recording the way that proof search happened in the system, and it basically just shows you, if you kind of read down the right-hand side of the equals sign, which rules were applied, and then the variables that it's applying to give you this ability to kind of track the dependency throughout the computation from the ones that were generated. So when we apply swap to like x1 and x2, then that gives us some facts that the rule produces, and those are named by the variables x1 prime and x2 prime on the left-hand side of the equal sign. Of course, in addition, we also get the solutions to the variables that were in our query, hopefully in the right order. All right, so that was kind of a toy example just to go through all of the components of Celf, all of the sort of end-to-end way that it works. So this is just going to be a more, just an example of something with several rules in the definition, which is, and I'm not going to go into as much detail about explaining how you set up the initial state and run the queries. Just trying to describe the rules of chess, sort of the way that things can move and capture. This isn't, I guess I want to make sure that you realize I'm not trying to describe like a smart AI for playing chess or something. And it's just a system that describes how the game works. Okay, so I've grouped pieces into 3 different classes. So they're the pieces that move like the king and the knight, which are basically only concerned with their source and destination cells. Those are kind of the easy cases. Then there's the pieces that can kind of move arbitrary distances in any direction if those are free. Those are a little bit more complex to code up. They use the same trick. And then there's pawns, which are just kind of weird. So I will go through this. By the way, I don't actually play chess, so I'm going to be embarrassed if I get something wrong, but you can just pretend that I'm talking about something that isn't chess. It doesn't really matter. Okay. Okay, so why did I lose that slide? Oh my gosh, this is terrible. I'm sorry. Okay, well, okay. Well, I can see, I can look through my album of slides, but I don't think that's, yeah, I think I'm just gonna have to, no, I think we're just gonna have to deal. Okay, there were a lot of rules anyway, and it's a little bit tedious. So, okay, no, but capturing was I was going to talk about movement before capturing, but they're basically identical except for the parts that I have in boxes. So let's start with capturing. Okay, so just ignore the first rule for a sec. All right, so the capture rule. So first of all, I guess this slide was introducing the concept of turns. So maybe I should point at the first rule. So the way that the rule is structured to allow for swapping turns between the two colors of players is we have some fact in our global state that says whose turn it is, and then we have some backward chaining, just simple fact that says the colors are opposites of each other. And then we do whatever the thing is that happens in a single turn, and then we conjoin the resulting state with the fact that the turn is now the new color. I think it's pretty straightforward. And the capture rule. So we need to consume this turn token, and so then we look at the fact, I'm using OCC short for occupied. So like the space P, the position P, I guess, is occupied by king of the color, and one hop away. So we have some separately defined backward chaining predicate describing the spatial relation between cells. So one hop away from P is P prime, and P prime is occupied by some piece of the opposing color. So then we transition to it being that color's turn, and now the king is occupying the new space P prime, and the old space P is now empty, and the piece of the new color is captured. So queen, and so this kind of like n-ary movement is a little bit trickier to talk about. So it's actually going to happen in 3 rules, and this is the first of them. So this is just the queen committing to a direction that she's going to travel. So it's the turn is color. The queen is in the position P of that color. The P prime is in direction dir from P, and that P prime is empty. So then now we transition to, okay, now the old space is empty, the new space is occupied with the queen, and also there's this additional, so instead of replacing turn color with turn color prime, it's now kind of like the middle of a turn. So we have this other predicate moving, which says now the queen is moving, the queen of that color is moving along that direction. Okay, these are just the remaining rules that describe queen's movement, so you can continue, which looks exactly like the initial commit rule, except that we consume moving in a direction, and we make sure that the new cell that we're moving to, P prime, is in that same direction that we were already moving. Then we can stop, which is just taking the fact that the queen is moving and transitioning to the other player's turn. And finally, we can capture, which again looks fairly similar to the movement rule, except instead of requiring the piece that we want to move to be empty, we specify that there's a piece there of the opposite color, and then we transition to a situation where that piece is captured. And of course, change whose turn it is. Okay. Pawn movement is, so this is just the final little like trick that I wanted to mention, just because it requires having this extra information that we track for each pawn. Because I think like initially you can move it 2 spaces, but then for the rest of the game it can only move 1 space forward. Also, what was I going to say? Also, like forward is defined differently depending on color. So this predicate 1 forward has to know which color pawn we're talking about. Okay, so again, we say that the pawn of some ID, so also there are multiple of them, so we have to figure out which one we're talking about. So the pawn with some ID is in the space P with the color, and it has not been moved yet. And then in that case, we can go 1 forward to get P prime, and 1 forward from P prime to get P double prime, check that both of them are empty, and finally set up the state so that it's now there and its status has been set to moved. So this is just to sort of illustrate that like we don't really necessarily need to group all of the properties of a pawn as one predicate talking about everything. It's like there are little pieces of the state and they each get represented by their own predicate. Okay, and then this is just the simple rule which says no matter which state we're in, we can always move 1 forward. And we as long as we make sure that, so if our status beforehand is S, then we need to make sure that the status after the fact is moved in any case. Okay, pawn capture I think should be straightforward enough that you could do it with what you've seen so far. If that's not the case, then I haven't explained it well, and maybe talk to me afterward. Okay. Okay, so what's the result of having, if you actually go through all the lengths of coding all this up and like setting up the initial state and figuring out how to do a query, then what you get is actually, like Tom mentioned this in his talk too, you get random games of chess. I don't know if that's super interesting, but it's illustrative of the point. I do actually think it's interesting in the sense of like, if you are designing a game as opposed to just trying to like write down a game someone else made, then you could do this to kind of see what the space is of available kind of playthroughs of your game, and maybe notice some things about your mechanics that you can tweak and experiment with before you code them up in some fancy C++ system or whatever. All right, so the takeaway just from this core example part of the talk is that linear logic programming can be can ignore those curly braces, sorry. The linear logic programming can be used to model this kind of local state on evolving systems. Okay, so now I want to tell you about like specifically what I think is cool about this. There are a bunch of people doing really interesting things that I've learned a little bit about. So linear logic, this kind of style is a lot like planning, and I know that some people have considered it as an alternative to planning in certain situations. Lucas Dixon did some work on dialogue planning with linear logic. Some other folks related to CMU, Henry DeYoung and Carsten Sherman, have used linear logic to describe voting protocols. Published at VoteID in 2011. Rob Simmons has used this to describe the operational semantics of programming languages using these concepts and a few of the other ones that Celf has. And there's also this really cool project that uses this to program ensembles of little cube robots that can form shapes that you specify just by performing computations locally, which is cool. So one of the things that I've worked on is using this for computational narratology. So this is a field that's kind of new to me, but I found some colleagues at Tuesday University who were doing this, again, sort of considering linear logic as an alternative to planning. And we used this system to describe all of the narrative events in the French novel Madame Bovary. And we just had 35 linear logic rules kind of describing the scenes of the novel. And then we used Celf's non-determinism to let this generate random stories for us, random variations on the novel, which is kind of cool. Narrative generation, I guess, is a fairly active field, and people have mostly just kind of used these ad hoc planning systems for it. So we were excited to try to apply linear logic in this context. And another cool thing that we can do with this is because we get this proof out, which is an artifact that it has structure, we can analyze. We can actually make graphs of causality. So each of the nodes in the graph is like some narrative event, and the edges are inferred by this external system that sort of describe which things that happened caused which other things that happened. And you can actually do some additional analysis. Like if you run this a bunch of times, look at several of these graphs, you can analyze them for some notion of equivalence and similarity, and then ask questions like, well, in all variants of the story, did this event happen? Or in all variants of the story, did this event always cause this one, or something like that? Okay, what I actually want to be able to do is use this to describe interactive fiction. So we sort of used it to describe generated stories, branching stories. But I like games and interactivity, and I want to use linear logic or some sort of extension of these ideas for hypertext and virtual worlds, or you can kind of think of the interactivity as just more atoms being thrown into the state when the user interacts. So the sort of first step of this would be when you run a program to Quiescence, okay, so grab the state of the world, throw in, take some key process or some other user input, and now the system, there's some more rules that can fire in the system. So now run it again to Quiescence and sort of do this in an interactive loop. Further aspirations for this would be to kind of be able to do that programmatically. Say there's some rules over here, I have some subset of my program over here that I want to run to Quiescence, and then use the rules from some other part of my program over here, throw them together, and combine them. So this is like adding phases, which is part of my PhD work. And another thing that I'd really like to do is add some way of doing meta theory, which is a kind of concept from logical frameworks, where we want to actually write down things, proofs, or write down statements that a system can prove for us, or write down proofs that the system can check for us, that certain things always hold. Like a really simple example of this would be, if our rules look like this, then there's some invariant of the state, which is that there's always exactly one of the green dot or the blue dot. And finally, I guess I'm a little bit out of time, but I wanted to give some historical context to this. I didn't invent linear logic programming. I like it, and I'm trying to extend the ideas and use it for things. But linear logic was invented in 1987 by Jean-Yves Girard. Prolog's been around since '72, and a lot of this work is inspired by LF, which stands for logical framework, so the idea of having like a proof system. And these ideas kind of all influenced each other. Actually, I realized after the fact that this is kind of the same form as the narrative causality graph that I had drawn before. So these things all fed into the idea of CLF, which is the formal system, and Celf, which is the implementation. And there's me. I'm interested in narrative interactive systems. I'm trying to put this all together. So I hope you enjoyed that. And there is code for Celf available that you can use. And once I get the internet working again, I'm going to put the examples from this talk there. And you can find me there. Thanks very much.